Okay, so hi everyone. Welcome to this South American geometry webinar. Just a quick reminder, if you wish to subscribe to our mailing list, you can send the word webinar to our email, or if you wish to join the WhatsApp group for talk announcements, you just have to click as found in the chat, as well as check our calendar for upcoming events. We have the whole semester already booked, so you can check the calendars there, as well as our previously recorded talks, which are available on our YouTube channel. Finally, this is a new feature. If you wish to subscribe to the Google Agenda directly so that it appears on your Google Calendar, you can click this ridiculously long link, which will add it to your Google Agenda as well. So this afternoon, we have the pleasure to welcome Rafael Montezuma from Federal University of Ceará, telling us about min-max widths in Riemannian geometry. Rafael, thank you so much for being here. Let's do 50 minutes plus discussion. I believe you're muted, though. Rafael, I think you're mute.
Yes.
Go ahead.
Can you hear me now?
Yes, but we do, however, see the we're not seeing on full screen. Now we do.
Now it's good.
Go ahead.
Perfect. Thank you very much for having me, for inviting me. It's very nice to speak in this online seminar. It's I'm happy to see that the seminar is still very crowded, even almost 2 years after classes resumed in presence, right? It's very nice to still have this seminar running online and very active. I'm happy to come back to speak about this topic. And so my title, as Henrique mentioned, is about some min-max widths in Riemannian geometry. But there's a connection with another notion of width, which is very classical for plane curves. And I would like to talk a little bit about this introduction on plane curves of constant width, just to try to make the bridge to the things that we want to do later. So to remember what this notion is, we consider a closed curve. Here we're considering omega is a compact regular domain. Here is the boundary of omega, as in this picture here. So we can take for any given unit direction that we denote by u of theta. So for each theta, which is an angle from 0 to 2 pi, you consider this unit vector in the plane pointing in some direction, making angle theta with some fixed direction. And fixed theta, you can consider this number, which is w theta, which is defined by this picture as the width of the curve in the direction of the vector u theta. That's by definition, by this picture, you can see it's the distance between two parallel lines, which are the very tight, enclosing the curve. So it's not possible to take two parallel curves which are perpendicular to this direction u theta, containing the curve, which is the boundary of omega, which are closer than these two. So this number, which is the distance between these two lines perpendicular to u theta, that's the width of the curve in the direction theta. And if you take if you vary theta and take the minimum width, that's going to be the width of the curve. It's just the minimum width as you rotate. I didn't say before, but if you have any questions, I'm not seeing the Google Meet window, but you can, if someone has a question, please let me know. So
about that, if people are not familiar with Google Meet, there's a little hand you can raise at the bottom of your screen, and I'll be happy to forward the question to Rafael because he cannot see you. Please go ahead, Rafael.
Thank you, Henrique. So just to move on this notion of a width, we can define an auxiliary function which we call pedal function. Assuming now that the domain is convex or strictly convex, we can use this pedal function, which is just the maximum value of the inner product of any vector in this domain omega with the direction u theta. If you maximize this, then this maximum is attained at a unique point of the region, which is a point that we indicate here, x theta. So x theta is the point, it's like the highest point in the direction u theta. So here we are indicating two values of this function. So p of theta is the pedal function, and it's realized at the point x theta. And here, if you rotate this vector by pi, then this would be the other. So the x of theta plus pi is this other point of intersection, considering the intersection of those two lines which are parallel to each other, and one arises as you maximize the inner product of x with u theta, and the other one arises as you maximize x inner product with the other vector, which is the negative. It's just the negative of u theta. So here we indicate these 2 points, and of course, if the curve is strictly convex, you can use this function p to parameterize the whole curve, and you can parameterize this way. So you can at each point, u theta and its derivative forms an orthonormal basis of the plane, and the two components of the points x theta in this basis are exactly the pedal function and its derivative. And you can also use the pedal function, so the sum of the pedal function at theta and theta plus pi, that's just the width, the distance between these two lines. So you can use this function p to parameterize the curve and to describe its width. So with this, we can define what we mean by, actually we didn't need this, but we can say more things if we use this parameterization. So a plane curve of constant width is a curve as above the boundary of some region. So we're considering here a curve which is a convex, which is parameterized as above by this function p theta, which is a periodic function of period 2 pi, such that we have two conditions. This condition here, p theta plus the second derivative is bigger than or equal to 0. That's just the convexity of the curve. So 1 over this sum here is exactly the curvature of the curve x. And also, if you want this curve to have a constant width, then that function w of theta must be constant. So the sum of p at a point theta plus p at a point theta plus pi is a constant, must be a constant. So here we have some, in the pictures, we have some examples. There are many, many examples of different sorts of plane curves of constant width. Is a very classical topic, and it has been generalized to higher dimensions and in many settings. People from different fields study these objects, such as in combinatorics or discrete geometry and so on, analysis. So here I want to point out some basic facts about curves of constant width. So the first is to illustrate the spirit of inequality that we are looking for. So it's an inequality relating the width. It's for a general convex curve. It relates the width and the perimeter of the curve, so the length of the boundary. Right? So it's the width of the boundary divided by the perimeter. This is for plane curves. This quotient is always bounded from above by 1 over pi, and the equality holds if and only if the curve has constant width. So this is a straightforward consequence. You can use the formulas, the parameterization that we had before to show that actually you have this more general property, which is that the integral of the width, the function which computes the width at each direction, as you rotate this angle on the circle, the integral is exactly 2 times the perimeter. So it follows from this, it follows that the minimum times the length of the circle is bounded from above by 2 times the perimeter, and then you get the inequality. So I'm also pointing out that just the equality case, perimeter equals pi times the width. In the case of curves of constant width, plane curves of constant width, this is known as Barbier's theorem. So these are some facts. So this is one fact actually, and just explanation. So the other fact is that going further on the examples that exist, I'm not going to go in details, but I just want to point out that there are many examples of plane curves of constant width, including examples without any symmetries. So Filmer is the name of a person who studied possible symmetries and also constructed examples of such curves without symmetries. So this is another basic, very simple property of these curves. So if you assume further that a curve of constant width, it has a central symmetry, so then it must be a circle. So circles centered at the origin are the only curves of constant width which are invariant by this involution, by the map that takes x to minus x. So just to close this part, this introduction, talking about curves of plane curves, I just want to point out that what we want to do next is to generalize these notions, these two notions that we have. So here in the case of plane curves is basically it's natural to consider the second, which is plane curves of constant width, in terms of the first, because you already have for the width of curves in the plane, you already have a width in each direction. So, but what we want is to generalize these two notions. If you move on to a curve, an embedded closed curve in a Riemannian manifold, these two things are not necessarily the first answers the second. So we want to come up with a notion of a width, which is generalizing the width of plane curves, but also it has a related notion of curves of constant width. But it's different because, as I was saying, in the case of curves in Riemannian manifolds, you don't define the width as a minimum of a set of widths. So it's not straightforward what should be a curves of constant width. So we want to generalize these two notions, and the basic idea to define this notion is to consider an invariant, another geometric invariant, which is a natural critical value of the distance function defined on the space of pairs of points in the curve. So gamma is a curve, it's an embedded circle in the Riemannian manifold. And you consider this set P, which is made of all subsets of the curve made of 1 or 2 points. So we call this set the space of pairs of points, but the 2 points could be the same. And of course, topologically, this space is the same as you consider if you had considered just the subsets of the circle with 1 or 2 points. And what's not, if you think a little bit as an exercise, but we are going to try to explain this quickly in the next slide, is that this space is equivalent to the Möbius band. So we have a function which depends on pairs of points. So it's the distance function defined on this set, which is topologically a Möbius band. And the width that we are going to consider, which generalizes the classical notion, is going to be some critical value of this function. So just before we move on to some more definitions, let me just try to point out what's this correspondence between this set of pairs, the space of pairs, and the Möbius band. So here we are going to use this rectangle on the left to parameterize pairs of points in the circle. So here we have the circle. So for each angle theta from 0 to 2 pi, we are going to consider P and minus P, these two vectors, these 2 points in the circle, which are corresponding to this angle theta. And we're going to parameterize on this on the value of theta here on this axis theta. We are going to use this segment, this yellow segment here on the left, to parameterize all pairs of points on the circle which are of this form here. So 2 points which are equidistant from P and minus P. So this pair here is one example, and this other pair of points which are the points which are perpendicular in the plane. So P perp, and it's negative. So the pair made of these 2 points is exactly here in the middle of this yellow segment. So as you move from the bottom to top, you are parameterizing all pairs that are equidistant from negative P and P. So the first point is just the pair minus P, minus P, and the last one is just P and P. So as you move from here to here, you parameterize all those pairs. So here on the leftmost segment at theta equals 0, and on the rightmost segment, you would have the same 2 points P and negative P, but they have the reverse orientation. So as you go from this point to this, so these 2 sides of the rectangle are identified, but with opposite orientations. So that's why we have a Möbius band. This space is just a Möbius band. So since we understand the topology of this space, we can move on, and this just gives us a hope to produce this non-trivial critical point that we want. So the function that we consider now is, if gamma is an embedded circle in this complete Riemannian manifold M, we are going to use this capital D to denote the distance between these 2 points in the pair. If the pair is just P and P, the distance is just going to be 0. So the minimum of this function is just 0, and the maximum we represent by the diameter. So it's just the diameter of gamma, but not in gamma. It's the diameter on the ambient. It's the extrinsic diameter. So since if you consider, for example, if you collapse all pairs, all points which are just a point in itself, if you collapse them all, then you are identifying the boundary of the Möbius band, all the points together. That's just an RP2, and the distance function is just 0 on those points. So the distance function passes to a continuous function on RP2, and by Moss theory, you expect to have, you should have another critical point of this function, but we need to be cautious because this function has a non-local character, and especially if you have a pair of points for which you have more than one minimizing geodesic, then the function capital G is not going to be smooth around that pair. So you have you have to come up with this notion of critical point for which considers also the fact that this function is not necessarily smooth. So let me point out here, at least intuitively, what is going to be this notion of regular and critical points. So first of all, we're going to say that a pair PQ in so it's as a set here, it's just a set of 1 or 2 points contained in the curve. So it's as a point, it's just a point in capital P. So this is a regular point if there exists a pair of tangent vectors, so V1. So here is a picture. We have these 2 vectors. The green vectors are representing basically an extension of the vectors V1 tangent to the curve at P and V2 tangent at the curve at Q. So you extend these 2 vectors to vector fields, 2 vector fields along gamma, which are tangential. So if you deform a pair P prime Q prime, if you deform P prime Q prime in the direction of these 2 vectors, so P prime Q prime is a point close to PQ. If you deform P prime in the direction of V1 and Q prime in the direction of V2, then the distance must decrease in first order. So since the function is not smooth, this is not very precise, but what we mean is that if you take any minimizing geodesic joining these 2 points, then the first derivative of the length of this minimizing geodesic must be negative in this direction for all minimizing geodesics joining the 2 points.
Oh,
yes.
Just to be sure I understand, and that was great because we could see the previous slide. Yeah, so leave it there. So we could think of RP2 as, locally, let's look at the picture inside R3, and then take these first order variations as tangent variations to RP2, say, as locally inside R3 by, and then do the first order variation thinking of points of R3 projectively, right?
Yes.
This should probably be equivalent to what you're defining here, right? You're defining these incidence conditions on each point, but you're thinking of these guys as living collectively in RP2. Isn't this equivalent to taking some incidence condition directly on RP2? varying in the direction of V inside R3, and then taking the projective point associated to that as well?
Yeah, I think so. If I understand, you are considering instead of varying the 2 points, you are varying the points in RP2, right?
Correct.
Yes, yes, it's the same thing. Yes.
Okay, cool. Yes.
Yes.
Okay.
Yeah, you can do this away from the boundary, right? Because on the boundary, you don't have a tangent plane because on the boundary of the Möbius band, you have so this RP2 is degenerated as you identify the boundary. You don't have a tangent plane there because the tangent space is just a line.
Mm-hmm. Okay. Yeah.
The two tangent lines to the curve, they coincide. So, but yeah, I have a picture which brings that point into the presentation.
Okay. Cool.
So yeah. So here in the picture, for example, we see that if 2 points in the curve are very close to each other but are different, then they are regular points because there is just one geodesic which is minimizing connecting them. So it's just you just take 2 vectors like these in the picture to decrease the length in first order. For that specific geodesic, you don't need to worry about other minimizing geodesics because they do not exist. So when this is not possible, we say that the pair is a critical point. For example, we have a critical points in the following situations. We have so the pairs P and P are critical points of minimum, and the pairs PQ realizing the diameter, they are critical points of maximum. And if you want to consider this notion more in connection with the structure of the minimizing geodesics, then we have 2 examples which are which are good to have in mind. For example, if you have 2 points in the curve, so the circle here is just representing gamma, capital gamma. So if you have these 2 points and there is a minimizing geodesic between P and Q, joining P and Q, which is perpendicular on both extremities, then this pair PQ is a critical point because there is no way to decrease in first order the length of this curve. It doesn't matter if there are other minimizing geodesics. So another situation is this situation that you can imagine that you have a rotational surface. Oops. You have this surface of revolution, for example, and you take a curve here, which is, for example, the revolution of 1 point. So P and Q, they are connected by 2 minimizing geodesics. So there are 2 minimizing geodesics, 2 curves realizing whose length coincide with the distance between P and Q on the surface, on the ambient. So here the ambient is the surface. So we say that these 2 curves, these 2 minimizing geodesics are simultaneously stationary if there is if at both points P and Q there is the same ratio between the angles, these 2 angles between the curve gamma 1 and gamma 2 with gamma. With the curve gamma, capital gamma. So basically, it's these 2 conditions. So it's a condition on the tangent vectors of gamma 1 and gamma 2 at the point P, and gamma 1 and gamma 2 at the point Q. So you have the same constant here of the proportionality constant is the same. So basically, the ratio between these 2 angles is the same at both points. Then you have the same property as in the case of free boundary of this other situation here. So there is no way to decrease in first order the length of both curves, gamma 1 and gamma 2. So if one is decreased, the other one is increased in first order. So in this case, you also have a critical pair. So now we define the number that is going to be realized as a critical value of the distance And this is our min-max, our basic min-max quantity, which we call the width, also the width. And as we'll see, this is going to coincide with the width if the curve gamma is just a convex curve in the plane. So you consider, I'm sorry about the slides, they're going back and forth. So here in the picture, we have the basic objects that we need to define this constant, this invariant S of the curve gamma, which are the sweep outs. So the sweep outs are curves in, if you want, it's better to visualize. I think it can be good to visualize this in the Möbius band. So here in the picture, let me move on to the next slide, and then I come back to this one. So here we have an example of a curve. So this blue Möbius band is just the domain of our function, and we have this yellow curve joining two boundary points. So these two boundary points, they're points for which P1 and Q1 are equal. So P0 and Q0 are equal as well. And here in between, these 2 points are just, so for each point of this yellow curve, PT and QT, so this is just a pair of points in gamma. But so this curve here is not a sweep out, because this curve can be deformed to a curve which is totally contained on the boundary. So in other words, this curve disconnects the Möbius band. On the other hand, if you look at this curve right here, this yellow curve, this curve does not disconnect the Möbius band. It's still connecting two boundary points. So this is what we want to think of as a sweep out. So this curve cannot be deformed with extremities contained on the boundary on a curve which is completely contained on the boundary. So these are the sweep outs. And looking back at the curve, the pictures that we have are these. For example, examples of sweep outs are the curves that we constructed when we observed that the set P is a Möbius band. So you can start at a point, you can start with a pair here, P0 equals to Q0, and you can move P on one side and Q on the other side until they meet. So when they meet, you have another pair of points, which is just P1 equals to Q1. Another possibility is to leave Q0 fixed here as T varies, and you move P around the whole circle, not only half. So these two are examples of sweep outs. And if for each sweep out, you can think, for example, for each curve like this on the set P, you know that at the boundary points, the distance function is just 0. So for each of these curves, you maximize the function of the distance, and then you take the minimum over all non-trivial curves, all non-contractible curves, in the sense they are not contractible to a curve on the boundary. So that's the number S. Since this class, this homotopy class of curves is non-trivial, then this number is positive. This is the content of our first version of the min-max theorem, which says that in this general situation of a smoothly embedded circle in the complete Riemannian manifold, this number is positive, and it's realized as the distance of a critical pair, of a critical point. So, in particular, we can go back and see that since this number is realized as a critical point, and on the plane, there are no multiplicity so for every 2 points in the plane, there is just one minimizing geodesic, which is the line segment joining the 2 points. Then there is only one type of critical pair, which is the one joined by a free boundary geodesic segment. they're all minimizing. So you can use this to show that the two notions, they do coincide. This number S, if you compute at the boundary of a convex curve on the plane, it coincides with the minimum width. So the width of the curve, which is the minimum width, as you vary, as you rotate the directions. So the inequality, so S being lower than this minimum is easy because for every direction theta, you see that you can consider a sweep out starting, for example, at a pair of points, which is just 2 times this point right here. And then as you move, you take the boundaries, so the 2 boundary points of a segment, which is perpendicular to these 2 lines, to these 2 parallel lines. Or in other words, you take this segment here in the direction of u theta, and then you translate it in the orthogonal direction. So for all those segments, if you take the boundary points or the intersection with the boundary of the curve, the distance between them is always bounded by the width. So you have the inequality, and the equality you observe that it holds because you know that this number is realized. The number S is realized by a critical point, which must be something of this type, the width of some direction. So moving on, thinking about generalizing that those comparison results between, remember that we mentioned this, we were able to compare the width of a plane curve and the perimeter, and to classify the curves of constant width as those maximizing the quotient. So in general, we want to be able also to classify, to find characterizations of curves which realize these inequalities, which are straightforward even in the general setting. So S of gamma is just a critical value of the distance. The diameter is just the maximum of the function, so it's above any other critical point that you can think of. And it's not hard to see that half of the perimeter, so this L of gamma is just the length of the curve, it's just the perimeter if you were in the plane. So you have these inequalities, and it's exactly this comparison between this critical value S and the diameter, which allows us to answer the second question that we mentioned in the beginning, which is the notion, how you generalize the notion of curves of constant width. And this is exactly when this equality right here happens. So in the general setting, so consider gamma as before. There is no other restriction at this point. So if you have a continuous map, so remember that on the plane, a curve of constant width is the same as having, so you have the same width in all directions. So you have many pairs of points on the curve which realize the width. So each point corresponds to another point, which is a pair of points realizing the width. So here we have something very similar. So if you have a continuous map that goes from the curve to itself, such that for each point you have, for each x, you have phi of x, such that the distance between them is the diameter, then S equals the diameter. So for each point, you have a corresponding point such that they realize the diameter, then you have equality in this easy inequality right here. And conversely, almost conversely actually, if you have this equality, what you can show is that for every point on the curve, there is another point such that they are diametrically distant. There is another point such that the distance between them equals the diameter. So that's not the same thing as a converse to the first statement, because we don't have for each x and y which varies smoothly or continuously actually. But in one specific situation, which is very interesting, there are some other more technical details that we are not going to bring to your attention. But so actually, the technical details are not related to this remark, but to the situation where we consider this curve gamma being the boundary of a totally convex disk. So imagine that gamma is a curve on the surface. It doesn't have to be on a surface, but it must be the boundary of a totally convex embedded disk. It could be so that this disk could be smoothly embedded in some higher dimensional manifold. But you can also think of gamma contained in the surface and enclosing a disk which is convex, which is totally convex actually. This condition is also not very restrictive. So in this situation, we can show that if you have the equality between S and the diameter, then for every point X, you have a unique point Y, which are diametrically distant. In particular, from this uniqueness, you conclude that you have a continuous map. So you have an equivalence between S equals diameter and this condition of having many pairs of points realizing the diameter. So these are the two main questions that we wanted to answer, but of course, yes, so this is just to bring to your attention that for convex plane curves, these two numbers being equal, it's the same as the minimum and the maximum of the width W coinciding. So those plane curves of constant width are exactly curves such that the diameter equals the invariant S. So these two things we mentioned before, that in the case of plane curves, there are many examples of curves of constant width. And also we mentioned that if you restrict yourself to curves which are centrally symmetric, then the curve must be a circle. So actually we have a generalization of this result in the Riemannian setting. So showing that there's a generalization of the notions that were classical to the Riemannian setting. They also carry some results that you had on the plane. For example, we have this theorem. If you consider now that the curve is going to be the boundary of a totally convex disk, so that if the curve bounds a totally convex disk on a surface, and you have this property that for every 2 points on the curve, they are joined by a unique geodesic. For example, this is true if the curve is very small. It's contained in a small neighborhood of a point on the surface. So this is true. Every 2 points are joined by a unique geodesic, for example. Oops. And now we are going to generalize the result. If the whole disk admits an isometric involution without fixed boundary points, without fixed points on the boundary of omega, this circle, and this circle has the constant width condition, so the width equals the diameter, then basically this has to be a circle in the sense that this domain must be a geodesic ball. So the curve is just a geodesic sphere. So you can think that this condition that every 2 points on the boundary are joined by a unique geodesic as localizing the result that you had on the plane. So if you have this isometric evolution without fixed boundary points on the curve, so this is just saying that the curve is not on the center of the evolution, and you have the constant width property, then the curve is a ball. So it's the boundary of a ball. It's just a circle. It's a geodesic circle. So remember that we compared also. We also mentioned that the diameter is bounded by half of the length of gamma. And if you compare the first, so the invariant, so we had a 3 invariants, we have this S of gamma, diameter, and half of the length of the boundary, the perimeter. So what happens when these two coincide? So we noticed that these two coincide. This is also for in the general setting, you don't have to restrict yourself to a surface anymore. So the equality between these two holds if and only if, if and only if the distance between two boundary points, X and Y, 2 points, it's not boundary points because the curve is not the boundary of anything, right? It could be any curve, any closed curve. So for every pair of points, the distance between these 2 points on the curve equals the distance between them on the ambient. So the intrinsic distance on gamma, which is just the length. So these 2 points, they split gamma into 2 curves. The shorter one is a minimizing geodesic on the ambient. So in the case of surfaces, if you have a circle with this property on a sphere, for example, then if you consider any component of the sphere determined by the circle, this geodesic circle, any of these two components are what Gromov considered a Riemannian filling. So there is an important conjecture by Gromov related to Riemannian fillings, and what we are realizing here is that Riemannian fillings are connected to, are linked to this notion of having this this critical value coinciding with the boundary length, the length divided by 2. So in this case, it's the boundary because it's on a surface here in the case of the example. So yeah, so here it's just examples. There are many examples just to point out that you have many examples of curves satisfying this property on the sphere, for example. You can consider S2 G tilde being the Riemannian lift of any metric on RP2, where n gamma being a curve which is the lift. It's a curve which projects onto a simple closed curve, realizing the infimum of lengths of all non-trivial, non-homotopically trivial loops on RP2. So if you take a curve realizing which is the shortest closed non-trivial loop on RP2, if you lift to S2 and you lift the metric, so this curve on S2 is going to be a curve for which S equals the length divided by 2. So the last part, I don't have much time, maybe just 1 minute. So let me just mention that this type of comparison and classification result for curves with constant width, curves for which the invariant S coincides with the diameter, is connected to many other questions which are related to geometric inequalities, which give classification results based on variational quantities, as we saw. So maybe the one which is very classical is when you consider the first eigenvalue of the Laplacian. So let me not be let me skip some details. So in this inequality here proved by Hirsch, you have that the relationship between the first eigenvalue of the Laplacian times the area of a sphere is bounded by this this constant 8 pi, and the equality here is achieved exactly. So this is achieved. So this is an optimal inequality. This holds when S2 is round. And also there are results for more general surfaces, for example, considering metrics which maximize this product, lambda 1 times the area in the conformal class. So if a given metric is maximal for this product, then you have a conformal map from this surface to some canonical sphere of some dimension, where this, which is a harmonic map such that the coordinates are exactly eigenfunctions of lambda 1. So there are also many other results, many other characterization and classification results related to systoles, which are another, it's another class of variational quantities which are defined related to the lengths of geodesics or areas of minimal surfaces. Also, other min-max widths are related to areas of some minimal surfaces in three spaces. And you also have some inequalities relating these min-max widths of minimal surfaces with curvature, with scalar curvature, or with the volume of the ambient space. So I just, with these final slides, I mentioned that the things that we are looking for, they belong to this class of inequalities which can be used to describe or classify spaces, metrics, based on variational quantities. So yeah, I think I'm going to stop here. Thank you very much for attention. Let me leave.
All right, let's thank Rafael, please. If you have a microphone, you can clap on it. Otherwise, you can clap with the clapping tool. Have you got any questions or comments? Go ahead, Luis. Okay, you're excused. All right. So, any other questions or comments? If not, I have maybe a comment. Whenever you're doing Riemannian geometry, right, there's always a sort of subclass of particular interest, which are the sort of manifolds with symmetries, such as, you know, like homogeneous manifolds or flags or whatnot, right? One would imagine that this theory would have a particular face, right? It would take on a particular form on manifolds with symmetry. Perhaps it could prove slightly stronger versions of some of these theorems in that case, or perhaps one could express these bounds in terms of sort of linear algebraic information if you're using that to define your homogeneous manifold, right? Is this something that's being explored? It's quite a strong sort of aspect of a South American geometry, both in Brazil, Argentina, and elsewhere. There's this theory of homogeneous manifolds in general.
Yes, I understand. So in this setting that I just described here for most of the talk, we haven't been doing that. So, for example, in the one possible, so just to make sure that I understand the question, it would be something like this, right? That for plane curves, it is the easy case, right? For plane curves, then you have this equality, which is better, saying, for example, that so in general, we know that the best upper bound that we have for this inequality is 1/2, and we have equality in some cases. But if you move on to the plane, then you cannot achieve 1/2. The best you can have is 1/pi, right? So I think your question is, if you move on to other spaces, what would be the best constant, right?
For instance, yes. I suppose if you consider manifolds with symmetry, say some manifold G mod H, right, yes, for Lie groups, then you could specialize these bounds. So in terms of sort of algebraic invariance of G and H, could we maybe express these as beta bounds, right?
I understand. Yes.
Or can we actually do better, right? And actually bound the actual perimeter instead of bounding, the width relative to the perimeter. Can we actually bound the actual width or the perimeter in terms of the sort of the sort of algebraic information that comes from, say, these quotients, right? This is not unheard of in the Riemannian geometry of homogeneous spaces, but you seem to be coming from this sort of theory of curves and surfaces that bring in sort of a whole class of questions, which look like they would have a particular case for homogeneous manifolds, which I've never heard of. Right, and even the use of sweep-out methods, right? How can you adapt sweep-out methods to symmetries, right? To manifolds with symmetries? You'd certainly want to define, sweep-outs that respect the symmetries in some way, but still sweep it out so they could still be mapped, right? And the topology of these manifolds is well understood. The topology of maps from the circle into these manifolds is well understood in terms of So it appears to me that somewhat, if you respect the symmetry, you could apply the same toolkit to find results specifically in terms of the algebraic nature of these manifolds. And I've never heard anyone doing this. So your questions, the sort of whole program in the context of homogeneous manifolds could be something.
There are some things. So for minimal surfaces, this has been done in many cases for constructing, for example, minimal surface, free boundary minimal surfaces in the ball with symmetries. Right. But so usually they are not that I remember worried about the geometric inequalities, because in the beginning of the theory, these Mimax invariants, they were constructed mainly to construct minimal surfaces, as a tool for constructing minimal surfaces. And so people have been using these Mimax. So you only consider sweep outs by things with symmetry, right? So people do that, at least for minimal surfaces. There are some papers on that. And but I don't know if it would be interesting to study the related Mimax invariants. Yes,
I think that would be something very, very South American, I guess, because we have several groups that study different aspects of the question, and some really good specialists all over the place. So you haven't heard of people exploring this very far.
Yeah, that's right. Yeah, No, not the invariants. Yeah, not that I remember.
Okay. Cool. Interesting. Any more comments in the audience? Questions? Or if not, then let us please thank Rafael again.
Thank you.